over to Rémy. Rémy is a researcher at INRIA and has been a MATLAB maintainer for quite a while at this point. Will tell us about the recent very exciting PFR project. So Rémy, thank you very much. The floor is yours.
Hi, thank you. Can you hear me okay? On a
Yep.
sliding screen? Yes. Okay, so this talk is about a collaborative project to formalize a piece of math. So, and I will, at the end of the talk, speak a bit more about the probability aspects in the formalization of that piece of math. So it's all about the PFR conjecture. So first, what is it? So the Martin or polynomial Feynman-Ressa conjecture is a former conjecture and now a result in additive combinatorics. It states that if we have a subset of F2n, which is non-empty, and such that its size, well, the size of the set added to itself is less than k times its size, then something. Let's stop here. And so the set A is basically a set of binary numbers with n bits. And that set A plus A is the numbers that we obtain by adding any two numbers in A bitwise. So 0, 1, 0 plus 1, 1, 1 is 1, 0, 1. And so what we're looking at is a condition on the size of that set A plus A. And the idea is that if A is some random set of numbers, then when you add any two numbers, if you add two numbers of A, you find another one, and the number of numbers that you get that way is close to what is quadratic in the size of A. So in the conjecture, we suppose that we don't get quadratically many new numbers. We only get a linear number of them, so k times the size of A. So under those conditions, then the conjecture states that A can be covered by at most a polynomial number of in K. Here I wrote the result that was actually proven recently, but a polynomial number of K translates of a subspace H of F to N with the size of H smaller than the size of A. So the idea is that if the size of the set A plus A is linear, then A has to have some structure. So here represented by that conclusion with subspaces. So that's a result in additive combinatorics. For now, there is absolutely no probability in sight. To give a bit more of context about it, it was attributed to Martin, but we can find first mention in a paper by Ressa in '99, where there's also a first result where what I put in red here, the k to the 12 is not polynomial in that first result, but exponential in k. There was then a big improvement in 2012, and the result as is written on the slide is the one that was very, very recently proved by Gowers, Green, Manners, and Tao. And the archive paper was uploaded to archive on the 13th of November 2023. So a very recent and quite technical result about a conjecture that I've been said is an important conjecture. It's in a field I know nothing about. But what is more the focus of this talk is what happened next. Like on November 13, Tao also started a project to formalize the proof of PFR in Lean. And that project was actually completed very fast. And on December 5th, 3 weeks after the start of the project, the proof of the PFR conjecture was free in the Lean project. So now I want to talk a bit more about the project aspect and the collaborative project of that formalization effort. Because first, what happened in those 3 weeks? So first, it's not the project of one person starting to code something in Lean. There were 25 contributors who pushed some codes to the GitHub repository for the PFR project. There was a website for the project, GitHub repository with code, a blueprint, which is something I will talk more about in a few slides, including a dependency graph to see how all the lemmas relate to each other, and various means of coordinating and communicating, because 25 contributors is a lot. So there was a Zulik channel in which people discussed what they were doing, where people were claiming a result, saying, I want to prove that result. So the project involved also writing a detailed LaTeX proof for all the results that were formalized. Then people pushed many Lean definitions and lemmas. And now, after the end of the project, there are now several contributions to MATLAB from code of that project. So the focus here is really on the number of contributors, and that means that 25 contributors had to coordinate efficiently in a short time to be able to prove this as quickly as it was done. So how can that many people coordinate to formalizing a very new and actually technical results very fast? So the way it was organized is that there is a GitHub repository for the code with CI, so continuous integration, to check that whenever someone pushes code to the GitHub repository, then every proof still compiles. A change to a lemma in one file doesn't invalidate proofs in other files down the line, and everything is always workable. So people would contribute through a pull request, and anybody could just open a pull request for any lemma in the project. And I want to mention here that all the work, well, the vast majority of the work setting up all this, the repository, CI, and all the infrastructure around it, was done by Yael, who did a great job at that. And crucially, I think the project used the Lean blueprint tool, which is written by Patrick, and that I will detail a bit now. So how does it look like? At the core of the formalization project is a big LaTeX document. So actually not Lean, but LaTeX, where someone can write proofs and definitions and lemmas. And on top of that, you can add some special tags saying that some lemma uses a definition or uses another lemma. And then one of the things you get from that is such a graph. That's a graph from the PFR project 1 week after it started, with different colors. So we can see some green, that's things that were actually fully implemented in Lean. You can see some blue, which were things that were ready to be proved, because all the definitions they depended on were approved, or all the previous lemmas were approved. So if you were looking to contribute, you could just pick a blue circle and then prove that. And there's also some white, where something is missing before you can start working on it. That's interactive. When you click on one of those bubbles, you see the statements. That's from the LaTeX document. So I think I clicked on the blue one on the bottom here, so you can see that it's a theorem, and with links to the to a web page where there is that LaTeX document rendered, and also a link to the Lean documentation for the project. And that's the web page that renders the LaTeX document with all the lemmas, some check marks stating that they were approved at that time, etc. So, and yeah, well, and that's the graph today. So that's the graph today. There was an update in the meantime, so there is a new shade of green. There is the full, the dark green, meaning that everything above it is also implemented. So PFR, the actual conjecture, is a dark green bubble somewhere in the bottom right. We can see that there's still things that are not dark green on that graph. It's because even though the PFR conjecture has been fully proved and implemented in Lean, people don't want to stop. And so they have been adding corollaries and refinements. The k to the 12 in the statement I have written at the beginning has been improved to k to the 11. And there are some corollaries and related results that people are currently working on at the bottom of that graph. So it was really collaborative work, and I want to highlight a few things about it. First, a great thing with a collaborative math in Lean is that anybody can write a PR and prove a lemma, and then they make a PR to the project repository, and if Lean accepts it, then the proof is correct. You don't need to, well, you still need to check the proof the right statement, but you don't need to trust that person to accept the proof. You don't need to know they're a mathematician who doesn't make mistake in what they do, doesn't claim what they haven't proved. So you can just have the trust done for you on the Lean side. It was really great to be able to prove lemmas in any order in that blueprint. So in that graph here, you could pick any of the blue nodes that correspond more to what you know about and what your specialty is, and then prove that, and don't care about the other parts of the project if you don't want to. On the flip side, someone needs to write the blueprint, and Denstow did that very, very well and in a very detailed way. And so that's why we could just pick up a lemma and prove it, because it was, the proof was, the lemma was stated in granularity that was good for Lean code. That's why I think it's preferable if the person who writes the blueprint knows about Lean and knows how to code stuff in Lean, because the level of detail you use in the blueprint is not the same necessarily as in paper math. And unit coordination still. So it's distributed collaborative work, but still very much centralized. And I think a very good thing about that project, and that was instrumental in having a project that's progressed very fast, is that the reviewing process of Denstow was basically, if it builds, I merge. So there was no requirement to have clean code, or to, which means we could iterate very fast, and then if we want to merge parts of the project to Matlib, then we will have to clean everything, but that can be done later. Another remark about the project, I think one thing you need if you want to start a good collaborative project like that is a good reason for people to care and join. For this project, it was not an issue. The result itself is important. It was proposed by someone very well known, and so many people were involved. So where's the probability in all of that? So PFR is a result in additive combinatorics, and as I said already, I know almost nothing about it. And the probability is in tools used to quantify the relative size of sets, which was done using the Broussard distance, which is a notion related to entropy. And okay, here we hit the first issue with the formalization of the paper is that MATLAB has no definition of entropy. And so on the graph that I showed before, roughly the bottom half is the paper proving the conjecture plus the recent extensions at the bottom. And the top half is basic things about entropy. And I think in any project you start formalizing something, then you always realize there is some appendix of the paper that is elementary stuff, but it's just not there yet, and you have to add. So for that project, it was entropy. So entropy is this. So let's say that we have a calligraphic X, which is a finite measurable space, and we have a random variable taking values in that space. Then the entropy of X is minus the sum over the possible values of the probability that X takes that value times log of the same probability. And the Broussard distance that I mentioned on the last slide is constriction related to entropy defined when the random variables take value in a finite additive group, and which involve entropy of random variables and entropy of independent copies of random variables. So that's the object that was needed in the project. How is it related to the relative size of sets? Well, on a set, you can define uniform, on a finite set, you can define a uniform random variable, and then you can look at the Broussard distance between uniform random variables on two sets, and so that relates sets. I don't know why that's a good notion of distance between sets, and and for that you would need to look at the more additive combinatoric part of the paper, which I did not look at as much. So we need those notions. We need that some properties of the Broussard distance, like it's non-negative, there is crucially a triangle inequality. We also need convolutional relations of those. So what we need are many notions of measure theory, but MATLAB had all that already. Random variables, the law of a random variable, conditioning on other variables, some independence notions. All of that was in MATLAB, just so we could start at the entropy. So all of that was in MATLAB, but like it was in there's now a lot of measure theory in MATLAB, but it's all written in more generality than finite or countable spaces. It's okay. On top here, I've listed a lot of possible assumptions that we needed on the countable additive group G that was involved in many statements. We didn't need all those assumptions everywhere, but for example, we needed some lemmas in MATLAB wanted to know that whether G was a standard Borel space or whether it had a measurable addition. And when you think of the use case, which is finite groups where every single thing is measurable, then yeah, of course, it's a standard Borel space. I won't go into the definition of standard Borel space, but it's just a too complicated notion for the finite case. So you would like to not even see those type classes appear in your code if possible. So what was missing from MATLAB was a lot of lemmas and some instances needed to just be able to work with the finite case without adding all those type class arguments to every lemma. So one of the things we did in PFR is to define a new class, which is discrete measurable space. And for example, a countable, that class means that every set is measurable. A countable discrete measurable space is automatically a standard Borel space, and so you don't need to ever worry about it anymore. And we had to add many lemmas simplifying the general notions that were in MATLAB to the finite in the finite or countable cases. So what are other contributions from PFR related to probability? So, well, obviously entropy and Resa distance with conditional versions. Those lemmas and classes for finite or countable cases. Lemmas related to independent copies of random variables. A lot about uniform distributions on sets, which were just not in MATLAB. And a few improvements to transition kernels. So I will end it here, and I will put on the screen the list of people who contributed. They are presented here in the quite arbitrary GitHub order. So that's it. Thank you.
Thanks very much, Rémy. This is yeah, this is sort of a milestone project. It's really exciting to hear about it. So yeah, we've got time for questions. As before, please raise your hand. The Zoom reaction. I see a question from Kevin.
So I was following the project quite carefully during that 3-week period, but I've been more worried about other things since then, like my forthcoming term. But it's still active, right? People are still doing things. So what's exactly going on now?
Yes, well, people are first proving consequences of PFR, other results related to it that use the same tools that were developed. As I said, also, the way we have been doing things in PFR is not necessarily the cleanest way. Like the focus was more on getting things done fast, and so there's also some refactoring and moving things into MATLAB going on. Yeah, but mostly it's those extensions down there.
Is the plan to get all of it into MATLAB?
Most of it, I guess. Yes.
Great.
You're muted, Rob. We can't hear you.
I'm sorry. So I was first saying, are there any more questions? Forgetting to unmute myself. But I was also saying a reminder that we're happy to take questions by voice after the talks, and there is a sort of continuing chat about each talk on Zulip. So make sure that you join the Lean Zulip and the Lean Together 2024 stream if you haven't already. I still have a question from Tomas Uribe.
Yes, you said anybody can write a lemma and add it, but you still have to check the statement. Can you elaborate on the check the statement part?
Yeah, it happened to be once that I read the blueprints and implemented a lemma, including the statement, thinking it was the one from the blueprint, then pushed to the repository, and then Terence told me that actually I had implemented some particular case which was simpler, and so we really needed the full lemma in the more general case that was written. So you, before marking one of those bubbles as green, you need to check that you actually have all of it.
So was that an issue? Was the LaTeX already there, and the translation to lean.
Yeah, it was a case where the lemma was written in LaTeX, including proof, but there was no statement in lean. So I wrote the statement, made a mistake in the statement, proved the wrong statement, which was simpler than the intended one, and then pushed that.
I see. So somehow the key thing that you need before somebody else starts working on, say you have a toy project, for example, you want to prove Fermat's last theorem. The key fact is to write the LaTeX statement and the lean statement and the LaTeX proof, and then let other people start playing.
I guess for the most important statements, yes.
I might inject a question of my own here. One of the things that I always like to hear about when there's a big like landmark project like this is what parts were hard that shouldn't have been hard. But I think part of the point of doing things like this is to feel out the system a bit and see what needs to be changed so we can do even more. Do you have any thoughts there? Like what should have been easier?
Yes. So something that almost does not appear in the paper proof is creating copies of random variables in different spaces to have them all in the same space. And so
Are you finding that slide again? That was somehow the most subtle slide.
Which
the one that remarked that there was X, this one, yes. Independent copies of X and Y. This sounds like the kind of thing that we say all the time.
Yes, that's
formalizing might be tricky.
And before that, there are X and Y are two G-valued random variables that are not necessarily on the same sample space. Somehow, okay, those random variables are functions from some omega to G, but the omega doesn't matter. So a way to make it not matter in the code is to not talk about at all about random variables, but only about their laws. But then when you then the operations on the laws on those measures are not as nicely written in lean, and it gets cumbersome. So you have those two aspects: random variables or just measures, and it's not obvious which of those is the easier to use in any circumstance. If you use random variables, you have to explicitly go from one omega to another and care about something you should not care about. If you use measures, then you can not just write X plus Y, you have to say that it's the map of the addition on the product of the measures.
So you use omega, X primed minus Y primed doesn't type, X minus Y doesn't type check, right? But X primed, X primed is a function from omega X cross omega Y to G. Is that the idea?
Yeah, that's the idea. Yeah.
I see. Oh golly. And you got all this working.
Yeah.
And should there be a tactic doing this kind of thing? This is somehow what this is the heart of Rob's question then.
Mm-hmm.
Was this hard to do under the hood?
I'm not sure. I'm still thinking that perhaps just there is a way to make it work with only measures, like really say that we don't care about the sample space and just not have it here at all, and maybe just introduce a notation plus index m onto measures. That means this is the measure of the sum of two random variables with those measures.
So there's a way of there's a way of encapsulating the concept of a random variable that doesn't mention omega X at all. Is that what you're telling me?
Yeah, but most often we don't need that omega in those finite cases, because everything we will say about the random variable is just talking about its distribution. Like that entropy is about the probability that X takes some value, and that's it. If you just then abstract that X and just say I have a measure on the on calligraphic X and just use that as and just talk about that measure, you can go quite far, and that's what we do in a part of the project, but then it gets cumbersome in other ways, and so that's not what we do in other parts of the project. I don't know if there's a tactic somewhere that should help.
Okay, I think it's time for a coffee break. So thank you again, Rémy.